All right, in the previous few lectures, we started chapter number 2, and we talked of how can you view the sky, and we talked about the latitude and how you measure your latitude, and that dictates how much you see from the night sky, and we talked about seasons and the special points or the special location of what you can see in the first day of summer or winter or spring or autumn as well. What we're going to actually do today, we're going to finish chapter number 2 and we'll look at the review questions. Now here, what we have here is basically how the planets orbit the sun. Of course, the third planet here is the Earth. And we talked about the ecliptic. And we said the ecliptic is the orbit of the Earth around the sun, or the apparent orbit of the Earth around the sun. And as you see in our solar system here, all of these planets are exactly or almost in the ecliptic plane. Okay, so when you look at the solar system, it's not something which is a three-dimensional. It looks like a disk. And the closer the planet, the faster it is moving. The further, of course, the slowest it's orbiting the sun. So we're using the Earth in terms of measuring times and so on. The rotation, it gives us the day and night, and one full orbit around the sun will give us a full year. So that's basically how we view the planets orbiting the sun. Now there is something which we can see over the course of time, which is known as retrograde motion. And this retrograde motion comes as a result of the difference in the speed of the orbits around the sun. So for example, we're going to look at the Earth here as it orbits the sun. And we're going to look at the Mars as it orbits the Earth. Now, we look at a situation where Mars is ahead of the Earth. But the Earth is actually revolving faster around the sun than Mars. So as you can see here, Mars is ahead of us. Then at some point, the Earth catches up with Mars, and the Earth will move faster. So it seems that Mars basically is moving backward, and then it comes back again and it moves forward. This area here, or it's regarded as something that we call retrograde. In the past, this was used to be a puzzle, and we'll talk about that in chapter number 4 when we talked about the models and how they try to account for this. Now, this is actually, you can look here in this slide, and this is a photo of Mars, but that's not in one night. These are successive nights. And when you put all of these photos together, you actually see this effect here. And that was a puzzle long time ago. Now we understand that this comes because of the differences of the velocity of the planets around the sun. So the Earth moves faster, and that's how you see it. If someone at Venus and look at the Earth, they may actually see the same effect. So this is something that you can also spot in the sky. Now, and this happens with the outer planets for us, like Mars, Jupiter, Saturn, Uranus, and Neptune. But it's very clear for us here when we basically see this eastward motion along the ecliptic. So that's something that you can see in the night sky. Now, the inner planets for us, which is Mercury and Venus, okay, if we want to basically see them from here, we only can see them either during the morning, that means before daytime, that means we call it the morning sky, or we look at it in the evening. Now, the word planet itself, it's mean a wandering star. So long time ago, when they looked at the planet, they did not really look at them as being a planet, but they actually, it's a star. But there was something strange about these, because remember when we talked about constellation, in constellation we said it is a group of stars and they seem to move as one group. But when it comes to planet, you may actually see it at different location, like what you see here when we talked about Mars in the sky, namely because they're closer to us, the stars are further away, so we're not going to notice any of these. But the planets are close to us. So long time ago, the name planet itself means wandering star. بالعربي sometimes يقول نجوم السيارة. And this is something that you can see in the night sky. So now, if we want to spot Mercury, Mercury is closer to the sun. So if we want to see that, Mercury itself or Venus or any other planet, they do not produce light. They only reflect sunlight. So they do not basically produce light of their own. They only reflect that. So for us to see them, we actually have to see them when there is a contrast. That means in dark skies. And they have to be above our horizon. So Mercury appears at 28 degrees from the sun, and that makes it very hard for us to spot here. So the time that you can see it, it's either shortly after sunset or before sunrise. Now, after sunset, it has to be in the west, and before sunrise, it will be in the east. So you really have short time to view Mercury. Venus, on the other hand, makes an angle of 46 degrees. It's here. And it can be seen few hours after sunset in the west in some seasons, and before sunset in the east, depending on the seasons. Now, if we try to look at the brightness of the object relative to us here on the Earth, well, the brightest object that you can see in the sky is the sun. And during the daytime, you do not see any stars or anything. You only see the sun. but sometimes we can see the moon, and we'll talk about that in chapter number 3. Now, planets, you cannot see them during the daytime, but sometimes when we call a transit, that means when the planet like Mercury or Venus is transit the sun during the day, so we can see a black dot on the sun. But at all the times you see things at night. So during the day we see the sun. And the sun, I think, is the brightest object relative to us here that we see. The second brightest object that we can see in the night sky is the moon. And we'll discuss that in chapter number 3. The third brightest object that you can see in the night sky is Venus. It looks very luminous. And the reason for that, as I told you, Venus has a thick atmosphere made of sulfuric acid, so it reflects light nicely, and that's why, and of course it's closer to us here, and that's why we see it as a bright object in the sky when it appears. We're just basically discussing what we see in the sky, and this is basically part of it. The planets, as I told you, you actually see them at different location during different nights and so on, and relative to the sky they may basically start changing their location, and that's why we call them wandering stars. Is this clear? Any question on these? Finally, we're going to look at the effect of the motions of the Earth on the climate. So remember, in the last few lectures, we talked that the Earth makes one full revolution around the Sun in a year. It makes one full rotation around its axis once every day. And due to its to the pullage around the equator, the gravitational pull from the Sun and the Moon tilts the axis of rotation, like I gave you the example of the top, and that makes the axis of rotation precesses around the normal to the orbit of the Earth around the Sun, and this precession takes 26,000 years. Now, the way the Earth orbits the Sun, if the Sun is here and the Earth orbits the Sun, this orbit is not circular. It's nearly circular. It is elliptical. So when you have a circle, you actually have a center. I'm not good at drawing that, but when you have an ellipse, you don't have a center. You have what we call one focus here and one focus there, so we call it two foci. Now, in the case of the Earth, it could be these two are very close to each other. So it's nearly circular, but it's not circular. It is elliptical. And that's why when we talked about the average distance between the Earth and the Sun, we said that the average distance is about 150 million kilometers. Now, when you deviate from a circle to elliptical, we can talk about something that we call eccentricity. And we'll explain that in chapter number 4. Now, this eccentricity, which is the orbit of the Earth around the Sun, it varies as well. So, meaning these 2 points here, or what we care that's very close to each other, they basically can vary as well, and they vary over a period of 100,000 years. And we already talked about the precession, and we said it takes 26,000 years. And the tilt which is now at 23.5 degrees, it varies between 22 and 24 degrees, and that basically over a period of 40,000 years. And I already told you in the last lecture, the tilt of the axis of rotation, it's the main reason for seasons, because we can have two seasons at the same time on the Earth. One in the northern hemisphere and one in the southern hemisphere, opposing one another. And this, of course, comes as a result of the tilt of the axis of rotation. So this will have an effect over time. And I told you, due to this precession, the seasons can be interchanged over time. Now, when we look at the Earth and you dig through the ice, you may actually come up to a conclusion that the Earth has went through times when the Earth was, especially the closer to the north and so on, went through a time where we call that ice ages. It's becoming very cold, and there are movies around that as well. So now, Morakovich made a hypothesis, and he said it changes in all these three aspects are responsible for the long-term global change, which we call ice ages. So that comes natural as a result of these, and that's why the Earth may go through these periods where it may affect. So the motions of the Earth here are has also an effect on the climate. Now you may hear a lot now about the global warming, and that basically comes as a result of a human activity, because we have an atmosphere, and the atmosphere is very important to us, and the atmosphere must have carbon dioxide and to trap heat. That's what gives us the comfortable temperature that we have. But if you put more, you will be trapping more heat, and the temperature may rise. And if it rises, then the polar caps, north and south, can be melted. And if they melt, of course, the water level will rise and so on, and will lose the dry land. So that's connected to our human activities. But there are things that do happen naturally because of how the Earth is moving. So, for example, if you look at this slide here, and you look at the Earth orbits today, and then you try to look at the precession and how the Earth is basically precessing, and you will see how the seasons are basically changing. So that's what's going to happen 5,000 years from now. That's what will happen 10,000 years from now, and so on. So you can see the effects here of how it's going to affect that. And in this slide here, we are talking about the last glaciation. That means when we had the ice age, and that's the end of the glaciation. And you can see in the diagram before here, time in years ago, and this is the ocean temperature in degrees Celsius, and you can see the red line here, which called predicted solar heatings, and here it says the observed ocean temperature, and you can see there is a correlation between these, and this is basically where happening due to these three effects on the climate of the Earth. So ice ages are something that normal that can happen on the surface of the Earth. With this, we can basically chapter number 2, where we basically talked about how we view the sky from the Earth, and we talked about the seasons of how we actually obtain the seasons. And then we talked about the different variation that the motions of the Earth can go through, and that basically can affect the climate of the Earth. Any questions so far? Any questions? So there are some misconceptions that people may fall into. Many people assume that stars are not in the sky during the daytime. I told you the stars are out there, but you do not see them because of what? Because the sun is very bright during the day. Many people insist that Polaris North Star is the brightest star in the sky, while actually this is not the brightest star that you can see in the sky, but it is a special star because it points very close to the north celestial pole. It's important, and I told you that will change over time. In 12,000 years from now, we will look at Vega as being the star, if we can live that long, as being the star closer to the north celestial pole. And there is a mix-up between revolution and rotation. These have different meanings. Rotation, when an object basically rotates around its axis. But a revolution, when you have an object which basically goes around a point. That's what a revolution is. So we say the Earth revolves around the sun, but it rotates around its axis of rotation. And the other misconception, many people think that the seasons occur because the Earth moves closer or further from the sun. Some can argue because the orbit of the Earth around the sun is elliptical. And I told you it is nearly circular. It's not that, the difference is about 1% or so. And that's why we say the average distance between the Earth and the sun is about 150 million kilometers. And the main, yes, the revolution is important of the Earth around the sun, because this is when the ecliptic, or the sun, is going to be either above the celestial equator, below the celestial equator, okay. And so it's important, but what the main reason that we see these seasons is basically due to the tilt of the axis, and that's why we can have two seasons at the same time on planet Earth. One is in the northern hemisphere and one is in the southern hemisphere. I think in Arabic, revolution, you can say left, and rotation is dawaran. So you can look at it that way. So even many people sometimes they use these words, but these words have really different meaning. When we talk about revolution, when we talk about rotation, when we talk about precession, okay. And sometimes there's something that we call circular motion. You really have to be careful with using these terms. And with this, we conclude chapter number 2. Are there any questions on chapter number 2? Well, the meaning of procession in Arabic, you can say tawaf. Okay? You can have it in this meaning here. Okay. Now, What we're going to do next is we're going to look at the review questions. And we have two sets for these review question. And as usual, the answer is given in red here. In one way of naming stars, a Greek letter indicates the brightness relative to the other stars in the constellation. I told you when we use alpha, beta, gamma, this is within the same constellation. That doesn't mean you can two different constellations and say alpha here and alpha here is equal. No, alpha in one constellation, that means it's the brightest star there. Two, a constellation must consist of a number of stars all within a boundary in the same general area of the sky. And I told you that these stars are not close to each other, but their projection happen to be in the same area of the stars. Although the constellation originated in Greek and Middle Eastern mythology, you know, the Babylonian, the Egyptians, and then the Greeks, and so on, most of the names are given in Latin. And the names of stars usually come from ancient Arabic. Now, there are many names of stars, sometimes in English, which basically have Arabic origin. Okay. But you may actually see them different. Now, is the brightest star in the constellation of Ursa Majoris? Remember, I told you the Little Dipper and the Bigger Dipper. They also have, the two names are Ursa Minor and Ursa Majoris. So the Alpha Ursa Majoris is the brightest star in the constellation of Ursa Majoris. Seen from northern latitude, the star Polaris always above the northern horizon. Whenever we discuss the horizon and you have a north on your horizon and you have no choice in choosing this north, it has to go up to the North Pole. And of course, on top of the North Pole is the North Celestial Pole in the sky. And if you find Polaris there, and that's basically where we say Polaris is above the northern horizon. That means the north on your horizon. 7, an observer on an Earth equator would find the celestial equator passing directly overhead. That's the only right answer here. Of course, he's not going to see that because we're imagining this celestial equator to be there. But if someone lives on the equator in the first day of spring or the first day of autumn at noontime, he or she will notice the sun at the zenith. 8, the celestial equator is a line around the sky above the equator. That's true. The dividing line between north and south celestial hemisphere, and I told you sphere, hemisphere means half of the sphere, and that's why we can talk about the northern hemisphere and the southern hemisphere. So actually these two answers are correct for number 8. The zenith is the point on the celestial sphere directly above any observer, and I told you the zenith is different for different locations, so it's not a fixed point. It's fixed only at a certain location, which is exactly on top of the head of the observer. An observer in the northern hemisphere watches the sky for several hours. Due to the motion of Earth, this observer notes that the stars near the North Celestial Pole will appear to move counterclockwise. Remember, we discussed this in the last lecture. We talked about clockwise, counterclockwise. So during the night, you notice that these constellation will actually rotate around in a counterclockwise direction. If you live at latitude 73 north, what is the angle between the northern horizon and the North Celestial Pole? Remember, we defined the latitude as the angle between the north on your horizon and the north celestial pole. And that's why we say here it is the angle between the northern horizon, that means the north on your horizon, and the north celestial pole. You live at latitude 39s south. What is the angle between the southern horizon and the south celestial pole? That means for someone who is on the southern hemisphere, they measure their latitude relative to the south celestial pole. So the angle there is 39 degrees. This is done here just to enforce the definition of what latitude is. 13, you live at latitude 28 degrees. What is the angle between the northern horizon and the north celestial pole? It is 28 degrees. You live at latitude 16 south. What is the angle between the southern horizon and the south celestial pole? It will be 16 degrees. If the celestial pole appears on your horizon, what is your latitude? Remember, I told you about the North Pole and the equator. Now, when you are on the equator, the North Celestial Pole will appear on top of your north. And that's why when you measure the angle between both of them, it will be 0. So at latitude 0, you may actually can see the North Celestial Pole, and opposite it will be the South Celestial Pole. So if you see the North Celestial Pole appearing on your horizon, that means you are at latitude 0, which means you are at the equator. Now here we are using a diagram, and in this diagram here, this is the north on your horizon, south, west, and east. And then they give you here the North Celestial Pole. Now what you see as the circle here is basically going to be the celestial equator, which cuts this in half. So now if you want to look at your latitude, the latitude is always measured as the angle between the North Celestial Pole and the north on your horizon. So if you look at this angle here, it's not 90 degrees and it's not 0. And above the middle, so probably about 50, but we say 50 north because it's measured relative to the north on the horizon and the North Celestial Pole. We can do the same thing here. If we look at our south on the horizon and the South Celestial Pole, and then you can measure the angle between both of them, and this will give you your latitude. So if you look at this angle here, it's not going to be 0, it's not going to be 90, but you have here 20 and 70. 70, it will be a little bit higher, so it's closer to 20. And we say here a 20 south because it's measured between the southern hemisphere and the south celestial pole. An observer in the northern hemisphere takes a time exposure photograph of the night sky. If the illustration depicts the photograph taken by the observer, which direction was the camera pointing? Remember what we talked about in the last lecture. When you look at the night sky, if you are in the northern hemisphere or if you are in the southern hemisphere, if you look, especially in the night sky, if you look north, the constellation will be going counterclockwise. And if you look east, they will be rising. And if you look south, they will be basically doing something like this. So if you are in the northern hemisphere and you see something like this, that means, and of course these are time-lapse, that means you're putting one photo after the other. That means the camera is pointing where? The camera is pointing south. Now again, if you are in the northern hemisphere and you see this, Now, if it's this way, that's rising. This is setting now. You have to be careful with that. And when you see this, setting actually happens when the camera is pointing where? Is pointing west. Now, in this case, you are in the southern hemisphere. And you see basically the star is circling this way. Well, that only happens if you're looking where? You're looking south. Now, if you're on the northern hemisphere, you have to look where? You have to look north. Now, you are in the southern hemisphere, and you see falling. That means the camera is pointing east. And if you are in the northern hemisphere, and you see the counterclockwise motion of the constellation, that means the camera is pointing where? Is pointing north. And I told you, you can use these things basically to tell time and to tell direction. Now, if you are in the southern hemisphere and you see rising for stars, okay, that means the camera is pointing where? Is pointing west. And remember what I told you, directions are opposite if you are in the southern hemisphere to what you have here in the northern hemisphere. And then we have a true, false here. The Greek created the constellation. That's false. Actually, the Babylonians, and that's what the recorded history says. Okay. The Greek letter designation conveys information about star location and brightness. Yes, within the constellation. Yes, that's true. The celestial equator always passes directly overhead. That's false. It only passes directly overhead for someone who is at the equator. And the celestial equator basically is imaginary. It's in the model of our own celestial sphere. And by the way, just to give you an idea, we see the sun, right? And the sun is 150 million kilometers away. But we see that on the night sky. And we see the stars, and the stars even further away. So as I told you, we imagine this celestial sphere. For the celestial equator always crosses the horizon at east point and west point. That's true. Navigators can find the latitude by measuring the angle from the northern horizon to the north celestial pole. That's true if they are on the northern hemisphere. And they can do that between the southern horizon and the south celestial pole if they are in the southern hemisphere. And as Earth rotates, circumpolar stars appear to be moving counterclockwise around the north celestial pole. And that's something that we see here if we are in the northern hemisphere. Again, as I told you, these questions here, it's like a review to test your understanding. Now, you really have to understand why this is the right answer. You don't memorize them. Okay. So that's the first set that we have here. Then we have another set, which is set 2. And in set 2 here, what causes summer here in the northern hemisphere is the Earth's northern hemisphere is tilted toward the sun. So that's the main reason. Revolution is important. That's why we go through seasons. But the main effect actually comes from the tilt of the axis of rotation of the Earth. 25. When it is winter in the northern hemisphere, it is summer in the southern hemisphere. The sun moves eastward along the ecliptic among the stars. Now, some of you may confuse this with the daily motion. If you look at the daily motion, the sun comes from the east and it moves toward the west. And that basically comes as a result of the rotation of the Earth. But the question here tells you among the stars. And some of you, they say, well, we don't see the stars during the day. But remember what I told you in the presentation of how we trace out the ecliptic of the sun. We look at the horoscope and we say, well, the sun is here, okay, in that location. So actually the sun, or the movement of the sun, is eastward among the stars. So I don't want you to confuse this. 7, which of the following causes seasons on the earth? Of course, the tilt of the earth's axis. 28, the summer solstice, which is the start of the summer, is the point on the ecliptic where it is furthest north of the celestial equator, halting its northward movement. Remember when we talked about the sun, and we said when the sun at 23.5 degrees above the celestial equator, that's when you actually going to get summer. And of course, it will move from that point. At the time of winter solstice, which is the start of winter, it is furthest south of the celestial equator. It's basically below the celestial equator. As seen from the Earth, sun appears to move eastward along the ecliptic among the stars. That's connected to the question we just did 2 questions away. So on the ecliptic, that's how it's moving. It's moving eastward. 31, at the time of winter, the start of winter, the sun is at the lower angle and thus is less intense than the start of the summer. We're getting less energy from the sun. Precession of the rotation axis of the earth is caused by, why do we get this precession? Is because the axis of rotation is tilted. And if the axis of rotation is tilted and the earth is rotating, you're going to get precession. So what caused that is the force of gravity from the sun and the moon's equatorial bulge. And I told you what the bulge is. It basically means the add. So this pull causes the axis of rotation to be tilted. And if it's tilted, we're going to get this precession here. I told you that if the earth is a nicely perfect sphere, then the axis of rotation, they're not going to be tilted. So there will be no precession. And at the same time, you will experience one season at your location. Okay. Because more or less, you will be at when we talk, the main season basically comes from the tilt. So that's something, but that's not what's happening. That's a hypothetical question. Precession of the rotation axis of the earth takes 26,000 years to complete a cycle. The ecliptic shape of the earth's orbit varies with time and takes 100,000 years. And we also talked about the tilt between 22 and 24, which take 40,000 years. In the Milankovitch theory, the elliptical shape of the Earth's orbit, its axis tilt and the axis of precession vary in time. These combined at times to create what? To create ice ages. 36. Does the appearance of the constellations follow a seasonal pattern? Yes, during summer night, many of the constellations that you see are different from those that you see in winter night. However, some constellations are visible all year long. And remember when we talked about horoscopes and so on, and I told you it depends on the seasons. 37. Which of the following statements correctly describes the relationship between stars and constellations? Every star is located in a constellation. Again, Remember when we talked about constellation, we said constellation is the brightest stars that happens to be in the same general area in the sky. A name is given and this constellation is used. But in astronomy, the sky is charted into 88 well-defined regions, and that region is called the constellation. So in that sense, every star is located in a constellation. Is this clear? How much of the night sky is north of the celestial equator? Well, the celestial equator cuts the sky into two halves, south and north, so we say exactly one half. 39, if you point toward the zenith, which is the point above your head right now, and then point there again 6 hours later, you will have pointed twice in the same direction relative to your horizon, because the zenith is exactly on top of your head. This is just to make sure that the point that above the head of the observer is always the zenith at his location or her location. 40, if an observer walks toward increasing latitude, the number of circumpolar stars will increase. So when you go higher and higher latitudes, well, you will see more and more of the northern sky, and that will increase the number of circumpolar stars for you. 41, if you were standing on Earth's equator, which of the following points in the sky would pass through your zenith at some point during one full 24 hours? Remember, we said that if you are at the equator, the sun will pass at the zenith at noontime and the first day of spring or the first day of autumn. So they make it general, 24 hours, and so actually vernal, and vernal is another name for spring. So when we have the vernal equinox. Now if I add here autumn equinox, and let's say I put it here as B, then the answer here should be B and C. But you only have one answer. Now with this, you can also reason how many times the sun could be at the zenith point for someone who's located at the equator over 1 year. Then in this case, you can say twice, because once during the spring equinox and once during the autumn equinox. Now, I can give you different times. I can give you, let's say, the time, let's say just before spring, and then I give you the time after the spring in next year. And I will tell you how many times. So you have one spring, and then you go around and have one fall, and then you pass and you get a spring, and then you go to that time. So we'll say 3 times. So you have to be careful with this. If the sun passes directly overhead on at least 1 day per year, then you are within 23.5 degrees latitude of the equator. Now you know that I told you if you are at 23.5, at noontime the sun will be on top of your head in the start of the summer. We are here in 24. We will experience that very shortly, and you can see basically no shadows. Very close to the start of summer. '43 in Brazil, and Brazil is in the southern hemisphere. It's not in the northern hemisphere. The longest period of daylight occurs during the month of, well, it will be in December, because in December they will have what they will have summer. But in December we will have what we'll have winter. 44, if you are standing at Earth's North Pole, Which of the following would be located at the zenith point? Well, the North Celestial Pole would be exactly on top of your head, and it would be located at the zenith. For stars in the same constellation, they may actually be very far away from each other. So you may see actually a constellation, and you think, even with the definition of astronomy that we have now, these stars are not located within the same distances from here. So they are maybe be far away from each other, but we see their projection. 46. During the month of June, the North Celestial Pole points toward Polaris. During the month of December, it points still toward Polaris. It's 6 months. Remember, I told you we need 26,000 years for a full cycle. So in 13,000 years, or it will basically get opposite to where it was. 47. If the Earth's period of rotation doubled, but the period of revolution stayed the same. Now we can tell day by the rotation of the Earth. So if you double the rotation, that means the Earth is moving faster, but you keep your revolution the same. Then what would happen is the night would be as half as long and the day will be as half as long. These are basically the review questions that we have for chapter number 2. The idea here is to understand why these are the right answers when you study them. So you're not just memorizing them. You have to understand why this is the right answer. Are there any questions on these? Is this clear? Is this clear? So with this, basically, we finish chapter 2 completely.